Okay, so in this problem we have to analyze the thermodynamic properties on this graph. So there's lots of different ways that thermodynamic properties can be visually represented. So it's important to look at what we are given here. Here we can see that the delta H is negative. So right off the bat, let's just say we know this must be an exothermic reaction. Furthermore, we can also see via T delta S, as temperature increases, T delta S gets more and more negative. So since temperature is absolute, this must mean that our delta S is also negative. So we're looking for a reaction that's exothermic with a negative change in entropy. So remember, there is a reaction class that you need to be familiar with and need to know that it's exothermic, and that is combustion. So anytime you have something with hydrogen or hydrocarbon react with oxygen and form water, and carbon dioxide in the case of a hydrocarbon, that's combustion. So this is an exothermic reaction, but here we're going from 2 moles of liquid and 25 moles of gas to a whopping 34 moles of gas. So that's going to be an increase in entropy, which eliminates this choice. You'll notice that we're given heat as a reactant in choice B and D. That's to show us that these are endothermic reactions, so we can eliminate those. And then choice C, we're going from 3 moles of gas to 2 moles of gas, so that's a decrease in entropy. And this is also combustion. It's combustion of hydrogen gas, so this is indeed exothermic. So this is the reaction that we're looking for here. Okay, up next we have a problem where we're given a Ka. The first thing I like to do is I like to see, is the stuff that we have in our problem, in this case sodium hypochlorite or bleach, the same thing that we're given a K for. So is this the same as that? And the answer is no, but they are awfully similar. Okay, and how are they related? Well, they're conjugate acid-base pairs. So sodium hypochlorite would dissociate into Na+, which does not affect the pH of a solution, and ClO-, which is the conjugate base of the weak acid that we're given. So, since it's the conjugate base of a weak acid, it must be a weak base. Therefore, it's going to do what all weak bases do in an aqueous solution, and it's going to hydrolyze water. So we have the reaction here. Hypochlorite plus water yields HClO and OH-. And since we have a solution of a weak acid, when in doubt, a weak base, when in doubt, ice it out. Yeah. So let's plug in the information we have. We have 0.7 molar ClO-. We don't care about water in these tables. This is 0. This is 0. The change will be minus x. Over here, plus x and plus x. 0 plus x is x. 0 plus x is x. And this is going to end up being 0.7 minus x. Okay, so that's 1/2 of our ICE adventure. The next thing we have to do is use this, we have to couple this with our equilibrium expression for fantastic results. So here, our products are HClO and hydroxide over our reactants, ClO-. Now wait a minute. Hydroxide, this isn't a Ka reaction. No, this is a Kb. This is a base hydrolysis happening here. So we're going to need to figure out the value for Kb. So we can use our relationship that Ka of a conjugate acid times Kb of its conjugate base equals Kw. At 25 degrees Celsius, this is equal to 1 times 10 to the negative 14th. So when we solve for Kb, we'll get that Kb of hypochlorite is 3.3 times 10 to the negative 7th. Cool. Now we have everything we need to know to answer this problem. So plugging in 3.3 times 10 to the negative 7th is equal to x times x squared. And remember, for the weak acids and weak bases we look at in this course, and considering that this is on order of 10 to the negative 7th, we can assume that the x is negligible compared to the 0.7 molar of hypochlorite that was there originally. So now we'll multiply the 0.7 through to get 2.3 times 10 to the negative 7th. Take some square roots. Take the square roots. And let's see what we get. We get 4.8 times 10 to the negative 4th. And remember, this is our concentration of hydroxide. So if we take the negative log of this, we're actually getting the POH. So let's do just that. It's 3.3, which means the pH at 25 degrees Celsius is equal to 14 minus that, which is going to be 10.7. So in this problem we have a solution initially consisting of ammonia and NH4Cl, which is just secretly in disguised ammonium salt that ends up being... Why, it was the conjugate acid the entire time! Now then, we're doing a titration into this combination of a weak conjugate base and acid pair. So we're starting off with a buffer, and then we're adding in hydroxide. It doesn't matter which strong base we use, right? Because this is just a source of hydroxide. So the key to this problem is asking ourselves, which of these two things will the hydroxide preferentially react with? Will it react with the basic component or the acidic component that has a proton to donate? Well, it's going to end up reacting with the acidic component. Okay? So let's move up to our reaction. Up there. So remember, by virtue of being a strong base, hydroxide is not going to react a little bit. Nay, it's going to be all like, give me all your protons. And it's going to keep ripping protons off of the weak acid component, which is why we use a full-headed arrow here. That's an arrow pointing towards an arrow, kind of an arrowception going on. And remember, whenever you have a titration, whenever we add a strong acid or a strong base in something, we're going to end up using an ICF table. And ICF tables are different from ICE tables in that, again, they react to completion, but also because they use what unit? That's right, moles. So remember that moles are equal to molarity times volume. So we happen to have a 250 milliliter solution. And 250 milliliters is equal to 0.25 liters. So let's multiply it by the molarity for both the ammonia and for the ammonium and see what we get for the moles. So for the ammonia, it's 0.3 times 0.25. So we're going to end up getting that we have 0.075 mole of ammonia. Now we need to do the same thing for the ammonium. And when we multiply the molarity of the ammonium by the 0.25 liters of the solution, we will get that there are 0.09 mole of ammonium. Great. So let's plug them into our ICF table and see what happens. Wait a minute, we're missing an important ingredient. We also need to know the moles of hydroxide that we're adding in. So we're going to do the exact same thing that we did before. And we'll get that there are 0.025 moles of hydroxide being titrated in to this solution. So let's just plug that in there. 0.025. Then we need to select the limiting reagent. Again, we don't care about water here. And our limiting reagent is going to be the one we have the least amount of on the left-hand side. So that's going to be our hydroxide. Minus 0.025. Minus 0.025. Meanwhile, in product land, plus 0.025. And that's going to leave us with 0.065 of that, 0 of that, we used up all of our hydroxide, and 0.10 mole of that. Wait a minute! that, the weak acid, it's conjugate weak base. Ah! We have ourselves a buffer! Whoop, 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 whoop. Neat. Buffers. Buffers are bae. Why? Well, they help us stay alive, which is pretty cool. But also, they make our lives easier as chemists because we can use our friend, the Henderson-Hasselbalch equation. pH is equal to pKa plus the log of base divided by acid. And remember, this is a robust equation. So we can plug in any units for the base and the acid as long as they are consistent. It's just the ratio of the base to the acid. Cool. So we can find the pKa. Let's solve for Ka. So we can use Ka times Kb equals Kw. When we do, we'll end up getting that Ka is equal to 5.56 times 10 to the negative 10th. Okay, now let's plug everything into Henderson-Hasselbalch and see what we get. So remember, P means the negative log, so pH is equal to the negative log of the Ka plus the log of the base, and I'm just going to plug in the moles of base that we have here, 0.1 over the acid, 0.065. Remember, it's perfectly fine to plug moles into Henderson-Hasselbalch. So our pH is going to equal the baseline for our buffer. The pKa is 9.25, and then our correction factor with the fact that we've got a little bit more of the base than the acid, that's going to modulate our pH up a little bit. This will end up being pH equals 9.44. Okay, we're doing some balancing here. I already have included the oxidation state of chromium in the dichromate ion, and then that of carbon in CO2. Just going to quickly work through the oxidation state of carbon in ethanol. So oxygen is in a -2 oxidation state. So again, I like to put the individual oxidation numbers on top and the total on bottom, since there's only one of them here though. It's the same number. Hydrogen is in its +1 oxidation state. There's 6 of them, so it's a total of +6. And now, since this whole thing is a neutral molecule, means when we add up everything, it needs to be neutral. So that means that carbon here must be in its -4 total, because -4 plus 6 plus -2 equals 0. And since there's 2 carbons, we're going to divide that by 2 to get the oxidation state on carbon individually, which is -2. Okay. Our first step in balancing redox reactions is to split into half reactions. So we can see that the dichromate, the chromium went from +6 to +3. So it was quite literally reduced. So that's going to be what we use for our reduction half reaction. So we have our CR2O7 2 minus, and it's turning into Cr3 plus. Neat. Okay, now for our oxidation reaction, we can see that carbon goes from -2 to +4. So carbon's going to be the star of our oxidation reaction. Now that we have these split into half reactions, I'm just going to take them one half reaction at a time. The first thing you always balance is anything other than carbon and oxygen. So here we've got 2 chromiums on this side, but only 1 on this side. That won't do, so we're going to put a 2 here. And then the next thing we want to balance is oxygen. So there are an impressive 7 oxygens on this ion and no oxygens over here, which means we need to add 7 waters. But uh-oh, now we have a whole new problem. Hydrogen's not balanced, but we can balance it using H+. So we've got 14 hydrogens on the right. We're going to add 14 H+'s here. The last thing we're always going to balance is electrons, and probably the easiest way to do it is to check the net charge on each side. Here we've got -2 plus 14 positive charges, so this side has a total charge of +12, whereas this side has a total charge, water's neutral, but chromium has a plus, each chromium has a +3 for a total +6, which means we would need 6 electrons in order to get these two sides balanced out. So now let's balance our oxidation half reaction. We have 2 carbons on the left, which means we're going to need 2 CO2s there. Now what's out of whack? Well, the oxygens. So we've got 2 times 2. We've got 4 oxygens on the right and only 1 on the left, so we're just going to add in 3 H2Os here. And then, well, now we've got 6 hydrogens from here and 6 hydrogens from here, which means we have a total of 12 hydrogens that are unaccounted for on the right so far. So we're just going to say plus 12 H+. And then once again, the final thing we're going to do is make sure that electrons are balanced, that charges are balanced on each side. This side has a net charge of 0. This side has a net charge of +12. That means we're going to need 12 electrons in order to have the sides be electrically balanced. So plus 12 electrons. Great. Now we're ready, well, almost ready, to combine and enjoy. But we need to make sure any self-respecting redox reaction needs to have an equal number of electrons in the reduction and the oxidation. So we can see that's not the case here, but all we have to do is multiply everything here by 2, and that will balance everything out. Now we are ready to combine and enjoy. So, in any properly balanced redox reaction, the electrons will always cancel out. Check. Then we do some other bookkeeping. So for example, there's 3 waters on the left-hand side. There's 14 over here, so I'm just going to change this to 11. Make things a little bit nicer from a bookkeeping standpoint. And then in terms of H pluses, there's 12 here and 28. That's an alarming amount right here. So we're going to subtract the 12, and this will end up being 16. Now we can combine. And upon combining, we get our balanced overall reaction. And we can see here that 16 is the coefficient in front of H+. Okay, so in this problem, we've got 5 different acids, and we're titrating them to the equivalence point. So just really quickly, by definition of the equivalence point, it's when you have an equivalent number of moles of whatever strong thing you're adding into your, in this case, acid. So because hydroxide is going to keep reacting, what happens by definition at an equivalence point is you use up all of the initial, in this case acid that we have, and all the titrant, and you end up with an equal number of moles of the conjugate. Okay? So, in all these problems, if we're titrating to the equivalence point, we're replacing all of the acid with its conjugate base. And remember, for acids and bases, for conjugates, Ka times Kb equals Kw, a constant. So that means the weaker the acid, the stronger the conjugate base that you're going to have left. Okay? So we're looking for which one will have the highest pH at the equivalence point. So we're looking for the weakest acid, because the weakest acid would form the strongest conjugate base. A few of these we can eliminate right off the bat. So this one right here and this one right here. Why can we eliminate those? Well, chloric acid and perchloric acid, those are strong acids. They're going to leave negligible conjugate bases. So in this case, the pH would be 7 at their equivalence points. But now we've got 3 possible candidates, and we're trying to find the weakest. So remember, for oxyacids, the rules are as follows. More oxygens means a stronger acid. And the more electronegative central atom you have, the stronger the acid. So these all have the same number of oxygens, 1, which means we need to rely on looking at the central atom. In this case, HIO is going to be the answer, because iodine is the least electronegative of those halogens, chlorine, bromine versus iodine. So it will be choice E. Anytime you have a problem where you're relating rates at different temperatures, you're going to be using this form of the Arrhenius equation, because this one has 2 different temperatures. And what it does is it tells us how many times faster a reaction is at temperature 1 than at temperature 2. Okay, because K is directly proportional to the rate. So what we're going to do here is, since K1 divided by K2 is how many times faster the reaction is at temperature 1, actually before we even plug in anything, I always like to declare T1 as the higher temperature. Okay, because these questions are generally always worded, how many times faster will reaction be? And higher temperatures means faster reactions, because you have more collisions, you have higher energy collisions, etc. So I'm going to say this is the higher temperature, and the higher temperature here is 333 K, which means T2 is the lower temperature, which is 303 K. Okay, now we're going to carefully plug everything in to our equation. So it's the natural log of, it says that it's 10 times faster at the higher temperature, so I'm just going to say 10 here is equal to activation energy. That's what we're solving for, divided by R, our gas constant. Activation energy is generally reported in kilojoules per mole, as we can see over our units on the side. So I'm going to use 0.008314 kilojoules per mole Kelvin here. And then 1 divided by T2, which is the lower temperature, 303 K, minus 1 divided by T1, which is our 333 Kelvin. My biggest piece of advice at this point is don't be a calculator superhero, okay? So just methodically go through and make sure that all of your calculations work, because it's easy to misplace a parenthesis or something like that here. So the first thing I like to do is I like to get rid of this whole mess of stuff inside the parentheses. So we'll do 1 divided by 303 minus 1 divided by 333, and this ends up being 0.000297. And the units on this will be K to the negative 1. Now, Let's plug in everything else. Okay, so units are very difficult to read here, sorry about that, but kelvins are going to cancel each other out, and then we can multiply each side by the 0.008314 kilojoules per mole, and divide each side by the 0.000297, and let's see what we end up getting. Our activation energy ends up being 64.46 kilojoules per mole. So it's going to be choice D. Okay, here we have a graph depicting, it's one of our three really important graphs from kinetics. So this graph represents the second order integrated rate law. And the reason why it does is if we look at the second order integrated rate law, we can see that it actually happens to be in slope-intercept form of linear algebra. That is to say, if we plot 1 divided by concentration versus time, we end up getting a linear plot where the slope is our rate constant k, and 1 divided by a sub 0 is our y-intercept. So, some important information we can draw out of this, first of all, is that it is indeed second order. That's going to be important. Next, we can say, well, the slope is equal to k, our rate constant, and that 1, so the y-intercept, is equal to 1 divided by a sub 0. Now we have all the information we need to answer this problem. Okie dokie. So, if we multiply through the a sub 0 and then divide each side by 1 molar to negative 1, we'll end up getting that a sub 0 is equal to 1 molar. And now let's plug everything into our second order integrated rate law. So 1 divided by concentration, which we see here in the problem prompt. We want to know how long it's going to take to get to 0.5 molar. So we're going to say 1 divided by 0.5 molar is equal to K, which is the 1 molar to negative 1 s to negative 1 times T. This is what we're solving for, plus 1 divided by concentration, the initial concentration that is, which is 1 molar. Okay, so over here we're going to end up getting 2 molar to the negative 1 is equal to 1 molar to negative 1 s to negative 1 times T plus 1 divided by 1 molar is just 1 molar to negative 1. We'll subtract that 1 molar to negative 1 from each side, and we'll get 1 molar to negative 1 s to negative 1 times T is equal to 1 molar to negative 1. So many 1's in this. And then we'll divide each side by our rate constant, which is just 1 m to negative 1 s to negative 1. This will cancel out. Seconds to negative 1 being in the denominator is going to flip up and become seconds. And our time here is going to equal dun, 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 1 second. So again, 1 seems to be the prevalent theme of this problem. Okay, so here we're given a veritable cavalcade of information here, and we're asked to find delta G. Okay, so how are we going to do that? Well, first things first, we need to find a way of relating this information back to thermodynamics. And to do that, we can use our K here. and one of our equations from thermodynamics, which is delta G standard equals negative RT times the natural log of KEQ. And this KEQ can be any type of K. It could be KA, KB, KC, KSP, KW, whatever. They all work. So let's figure out what delta G standard is in this case. Whammo! We plug in our values and we solve for delta G standard, and let's see what we get. So delta G standard is equal to 50.0, and that's going to be kilojoules per mole. Now, that's delta G standard, which is all well and good, but look at these wacky concentrations of things. Okay, oh, that's not a concentration. But look at these wacky concentrations of these. That's not 1 molar. These aren't standard conditions. We better invoke an equation that relates delta G to delta G standard under non-standard concentrations. But do we have an equation with that power? Why, yes. Yes, it's actually already written down here. Never mind. Whoop. All right. So let's use this and figure out what our delta G is. First things first, let's figure out what Q is. So Q is equal to our product of our reactants. So in this case, it's going to be the protonated pyridine, C5H5NH plus times the hydroxide concentration, all divided by the pyridine concentration, C5H5N. Now, most of these were explicitly given. So we're explicitly given the concentration for this and for this. Hydroxide, we're not explicitly given it, but we do have a way of finding it. Since our pH is 9.78 and we're at 298 K, that means we can subtract that value from 14 and get our pOH, which is equal to 4.22. Now we can figure out the hydroxide ion concentration. So the negative log of the hydroxide concentration is equal to 4.22. So we'll switch the negative sign to the other side. And then we'll do 10 to both powers. And we get that the hydroxide ion concentration is 6 times 10 to the negative fifth. So now let's plug everything in and solve for Q. So voila, there is our expression for Q with our numbers plugged in. And when it's all said and done, we can take our calculation and solve for Q. And Q is 6.03 times 10 to the negative 10th. Now we can plug everything into our equation over here, which will let us get our value for delta G under these non-standard concentrations. So here we have our equation with our delta G standard plugged in. Here we have our R, here we have our temperature, here we have our Q, and so here we have, it ends up being 50 kilojoules per mole plus negative 52.6 kilojoules per mole. And this will end up giving us our answer, which is delta G equals negative 2.6 kilojoules per mole. So this question is pertaining to voltaic cells. I'm just going to quickly draw a voltaic cell diagram here. So we've got one compartment. We've got another compartment. And we'll have two materials, usually metals, attached, and let's see here. So, just for this particular illustration, I'm going to make this side the anode. Doesn't necessarily have to be. This side the cathode. And let's talk about what happens. So, electrons always travel in alphabetical order. What I mean by that is they always go from A to C. They always travel from the anode to the cathode. So I'm going to annotate this by putting some electrons and an arrow to show which way they're migrating. They're migrating toward the cathode where reduction takes place. And ordinarily, if you had the electron flow like this, a negative charge would build up in the cathode really quickly. And would electrons want to travel to a negatively charged solution? Well, no. So this would short circuit within milliseconds. So we need something to help keep things electrically neutral. Enter our friend, dun 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 dun, the salt bridge. Okay, so I'm just going to use the classic salt bridge here of sodium nitrate, Na plus and NO3 minus. So the idea behind the salt bridge is that the cations will move into the cathode because that way the cathode doesn't build up a negative charge. The anions, on the other hand, will move into the anode. Because if electrons are leaving the anode, this side would build up a positive charge, and electrons wouldn't want to leave that. So the purpose of the salt bridge is to just maintain an electrical neutrality. And it does that by having the anions move to the anode and the cations move to the cathode. So now let's go through and discuss which of these are true and false. A, if a voltaic cell has positive cell potential, it is spontaneous as written and will have a negative delta G. Spontaneous does indeed mean a positive E cell and does indeed mean a negative delta G. Okay, this one is true. Okay, the next one says, in a voltaic cell, at equilibrium, E cell equals 0 and delta G equals 0. Yeah, that's also true. By definition of equilibrium, you have your ideal product-to-reactant ratio. The reaction isn't moving one way or the other, so delta G would be 0 and E cell would be 0. Now, E standard will still be the standard value for that cell, but E cell will be 0. C says, in order to maintain electrical neutrality in a voltaic cell, anions in a salt bridge flow toward the cathode. Ho-ho! We have our winner? I don't know. That's the appropriate one here. This is the false statement. But let's just go through the other ones, too, just for posterity's sake. Electrons in a voltaic cell always travel from the anode to the cathode. Oh, yeah. And then finally, during electrolysis, electrical work pulls electrons from the anode and forces electrons into the cathode. So even in electrolysis, electrons still travel from A to C. It's just we force that reaction to go. So this one is indeed true. So the only one that is false is choice C. Okay, for this problem, I'm first going to analyze this graph, and then we'll move forward to the actual problem. So there's a few things that we can take away from this. First of all, we can see that there is a net decrease in the potential energy. So this is an exergonic reaction. We can see that there are 3 hills. 1, 2, 3. Each hill represents an elementary step, so it's a 3-step reaction. And specifically, this second step here is the largest step. So because this one has the largest activation energy, that means that this is going to be the rate determining step. That's going to end up being important later on in this problem. Okay, so a few other things to point out. Activated complexes. Those are represented by the hilltops. Sometimes you'll also hear these called transition states. And then these valleys here represent the intermediates. So these are actually molecules that you could isolate from a reaction, whereas you can't do that with the transition states. Okay, so now let's go to the actual problem itself. As we stated before, the second step is the slow step. So that's significant because if we know that this is the slow step and we have an elementary, or we have a series of elementary reactions called a mechanism, we can come up with a rate law based off of that slow rate determining step. So that's exactly what I'm going to do. Rate is equal to some constant k, and then we've got N2O2 and O2. And now the question becomes, is this a good rate law? No, it is not. Why isn't it? Well, the problem here is that we have N2O2 in our rate law. And we can see that N2O2 is made in the first step and then it's used in the subsequent step. That means that's an intermediate. And remember, we cannot include intermediates in a rate law. But with the help of a little algebra, we can substitute it out of there. So while the first step is going really slow, while the second step is going really slow, remember the first step has a chance to reach equilibrium. So why is that significant that this reaches equilibrium? Well, at equilibrium, the forward rate and the reverse rate are equal to each other. So we're going to use that fact and then do a little substitution. So I'm going to write out the rate law for the forward first step. So B rate is equal to some constant K, I'm going to say Kf for forward, times NO times NO, let's just make it NO squared. And that's going to equal the reverse rate constant, Kr, times N2O2. Okay? So now our goal is to substitute the N2O2 out of our working rate law. So we can solve for N2O2 algebraically by dividing each side by K sub r. Constant divided by itself is just 1. Constant divided by a constant is, I'm going to actually sing this song again, a whole new constant. And you know what? We don't care what this constant is. We're not solving for it here. So I'm just going to call it K fun. Which is hard to see because I chose yellow there anyway. Anyway, it doesn't matter. Now that we've solved for N2O2, our intermediate, we can substitute into our rate law the NO. So we're going to take this whole thing and just plug it in. Again, we're giving N2O2 the intermediate the boot. And then when we do, we'll end up getting our final rate law, which will be a working rate law. It is rate is equal to some constant times a constant again, whole new constant. We'll call it K observed, OBS, times NO squared times O2. And that is a good rate law. Okay, that concludes practice exam 4B. You did it! Make sure to go forth and dominate that final exam. And please let us know if you have any questions. I hope you liked this video. Remember to like and subscribe for more content like this, etc., etc., etc.